Okay, great. Okay, hi guys, welcome. Good evening. Welcome to the live session for the Marvel course, and we'll today do a recap of what has been covered till week 4 lecture. Uh, those of you who are joining uh, new, my name is Manav. I'm a PhD student in the ECS department, and I am one of the TA for this course. So is my screen moving? Can you see the screen move, or is it stuck for you?
It's not moving.
Okay, okay. Let me change Wi-Fi connection. Okay, I think there's a bit of a lag from the screen that I'm presenting and what I'm saying. So I'll try to go slow now. So okay, we'll start off with one example problem. I think Aniket has already covered this when he took the live session last week. So you guys have done till now two problems on MDP modeling, but I'll give another problem to you guys. So this is sort of a take-home assignment because uh, after you design the MDP, you need to perform value iteration and show the optimal value for each state and many other tasks. So if you like, okay, you need to do this, and this. And these all are discussed in week 5. So it's better you take it home and we can discuss it when we start with the week 5 live session. Okay, screen is still stuck, it seems. Wait, let me reshare my screen. Maybe. Still not visible. You guys can see the screen, right? Okay, I'll take that as a yes and yeah, I'll continue. So, okay, I'll quickly read this problem. So, this is what the problem says. It's a word problem. So, so there's an undergrad student in a certain university, and the student has only three tasks to do. Okay, and sorry, the student has only two tasks. That is, it has to go attend class and eat food during tenure in college. So, assuming this is a residential college, so the student has only two tasks. A very simplified problem: either go attend class or have food and come back. And the student can access only three locations in the campus. First is that it can go to the hostel or stay in the academic building or go to the canteen. And on going to different places, it gets a certain reward. And there are certain probabilities by which the student can stay in the second paragraph covers the entire gives the entire model of the system or the university that the student is in. And then you information. The task you need to do is you need to design a finite MDT by of all the states actions and the corresponding transition probabilities to go from one state to another by taking action, and you record it in a tabular form, and then after that you try to perform your value iteration, show what is the optimal value for each state, then do the policy iteration and show what is the optimal policy, and then you need to discuss what the results you gain from value iteration and policy iteration. Hello, hello. Can you guys see my screen? Can you hear me? I think I got disconnected.
Yes, audible.
Okay, okay. I think this internet issue is going to persist here. I can't really help it. Uh, uh, I think it's very unstable right now. I won't be able to take a complete class with this. So is it okay if I end the meet now and record this entire thing and send it to you later?
Yeah, sure, Manav. That
I don't
works.
Yes.
think it will just take a lot of time just to get myself connected.
Yeah. Just record this
Can you
and
guys
put
hear
it
me?
on you. Put it on YouTube, and we can view this.
Uh, Sorry, I lost what you are saying. Uh, Hello. Yeah, can you guys hear me? So, what I
Yes, Manav.
suggest is I end the meet now because it will take a lot of time with this internet connectivity, and I'll record this live session and put it on YouTube if that is fine with you all.
Yes, sure.
For us.
Okay, sure. Okay, thank you guys. I'll do that then. And sorry for this issue. Okay,
No issues,
see
no
you. Bye.
issues. Bye.
Bye. Bye.
Hello, sir.
Yeah. Hello.
Yes, it will be available in YouTube.
Yes.
Hello.
So if you go to the NPTEL course tab and you look at the
Yeah.
problem solving session, you see all the live sessions are uploaded on YouTube, and you can find all the PDF lectures that I share here. That also will be available in that folder.
Okay, sir. Thanks, sir. Thank you
You
so
just
much.
need to go to the NPTEL page and
Course tab.
look at the problem solving session. Okay.
Okay, sir.
Yes. Okay. Thank you. Bye.
Thank you, sir.
Bye.
Hello. Good evening, guys. Sorry for the technical difficulty that I had with my internet connectivity. Unfortunately, I had to take it to the offline mode, and I really apologize for any inconvenience from my end. Hopefully, I try to cover what I had in mind for week 4. So, this will be a short recorded video. I'll try to quickly convey all the important points that had been covered in week 4. I think week 4 was not much content wise was covered. More on the mathematical proof and convergence theorems were uh, covered in week 4. So I'll try to give a brief overview, and on top of that, maybe we can look at few interesting toy examples and questions which we can carry on to later weeks as part of this course, so that you can also get some hands-on experience with reinforcement learning. Okay, so the standard introduction. Those of you who are joining for the first time, my name is Manav. I am a PhD student from IISER, Bhopal, and I primarily work in the area of multi-agent reinforcement learning uh, in applications to multi-robotic systems. If you have any overlap or if you find any point of commonality, you can get in contact with me. And okay, let's start. So the first thing that was covered in the course was on MDP modeling. So if you all had attended last week's Aniket's TA session, doubt clearing session for week 4, you would have noticed he covered 2 interesting MDP modeling problems. So I have another one. So this is sort of take home question. So if you see, along with that, I'm trying to jump a bit ahead. So in that MDP modeling question, I'm trying to also include some points that are covered in week 5. So since this is a take home question, I expect you all to by the time we meet next week, you are familiar with value iteration, policy iteration, and then we can discuss about this problem more in depth. Okay, so in addition to just designing the MDP, you guys need to perform value iteration and show the optimal value function for each state and the policy update. This is one thing you need to do. Second thing is, based on the design MDP, you need to perform policy iteration and show the optimal policy. And then third point is, you need to discuss the results which are obtained from the policy iteration and the value iteration. So these are three new things that you need to do. So I'll quickly read through the question. So the question is that I'll try to read through the word problem. So there is an undergrad student in a particular university, and the student has only two tasks. Okay, so it has a student. There is a student has only two tasks: either attend class or eat food. So this is a residential student. It lives in a campus like IIT Madras or IISM Bhopal. So it has only two jobs in its college life: either attend class or eat food. And the entire student life revolves only around three places. So you can think of it as three states. So the three places are the college canteen, then there's the academic area or the academic building, and third is the hostel. Okay, so the student can be found at any of these three places, and it has a job of performing only two activities. Based on that, it gets certain rewards on taking certain actions at certain states. And you guys need to basically read through this whole paragraph, design a proper finite state MDP, and write down all the possible transition probabilities. And then after that, once you are well versed week what has been covered, you need to answer these three questions. So this is the question that I had prepared, and if you want, you might refer to example 3.3 in Sutton and Bartow reinforcement learning. This is edition 2 of the book. Okay, so this is just a take-home question. You can play around with it. I'll quickly do a roundabout of what all has been covered in the week 4 lecture sessions. Okay, so professor had introduced the Bellman equations. So if I have for the value functions, for the action value function and the state-based value function. So for the state-based value function, it is represented by the variable v pi of s. This is nothing but the expected return given state s. So it measures the goodness of the state that the agent is currently at. So if you unroll this equation and you do it step by step, you will eventually end up with this long equation. This long equation is known as the Bellman equation. Okay, this long equation is known as the Bellman equation for v pi. Okay, similarly, if you look at the action-based value function, which is the q function, the q pi s of a is the expected return given state is if I take action a at state s. Okay, again, if you do a series of unrolling step by step, you'll eventually end up with this long equation. And this equation is the Bellman equation for q pi. Okay, so let's say I call this as equation 1 and I call this as equation 2. Okay. Just a quick look, you see from equation 1 and equation 2, you can see there is a nice relation between the v pi and the q pi function. Okay, so let's say call it as the relation between v pi and q pi. You can see that this is very intuitive because in the vpy function, I am summing over all possible actions that I can take in state S. Whereas in the queue function, I'm fixing the action that I'm supposed to take, and based on that, I'm computing the rest of the optimal value function, right? So this is the relation between these two functions. Now, just to give you some kind of an intuitive example, so I have taken a very toyish kind of an example. So imagine that you have a grid world environmental setup, and there's a robot here, and this is the starting position for the robot. And the robot needs to reach this green box over here. The robot needs to reach this green box over here, and if it reaches here, it gets a reward of +1. Okay. At every other place, it gets a reward of 0. But if it reaches the green box, it gets a reward of +1. But if it reaches this red box, okay, this fiery box, so it gets a reward of -1. And this particular box here is an obstacle. So the robot can't go here. Okay, this is a wall. Even if it tries to go there, it will not go there because it's a wall and there is no penalty for crashing into a wall. Okay, and so how do you go about thinking about it? Okay, so let's say you forget about Bellman equations. If you had no idea about what Bellman equation is, so if the robot reaches this particular state, okay, so this is the absolute best state, and it gets the maximum possible reward, which is a reward of +1. Okay, so let's say my robot is at this state currently. Okay, so the robot is in this box. It knows that if it takes the next action, which takes me to which goes to the right, okay, so I end up with the maximum possible reward. So if the robot somehow reaches this state, it knows action to take. It needs to go to the so in that case, it gets a value of 1. Okay. And similarly, if I go back to this particular state, okay, okay. Yeah, so if I go to this particular state, again, I know that if I reach this state, again, I know if I reach this state, I'm doing, so if I'm here, I again need to take direction to the right hand side, and then I'm good to go. And similarly, if you just need to keep on backtracking, assuming you don't know anything about the Bellman equation, you just need to keep backtracking until you reach the starting position, and then based on the initial position of the robot, it basically starts taking steps towards the goal direction. Okay, so you see the problem here is, let's say instead of starting from here, the robot, let's say, gets initialized at this box. Okay, now if the robot is initialized at this box, so it has two possible actions. One is to go right, or the second action is to go down. Okay, so this is the two possible actions that the robot has. But the catch here is that for each of the possible state that the agent can move to, it goes to the right or it goes to the down. So you see the problem is with initialization having just a naive right. So to tackle this, we use something known as a Bellman equation. Very roughly, the Bellman equation is written like this. Okay. So I know there can be some notational differences between what professor had used and what I had written in the previous slide, but this is the basic crux of the Bellman equation. So just giving you an intuitive idea of what this is all about. Uh, so what it does is it takes the reward of taking the action A at state S, and then it adds a discounted value of the value function of the next state that it reaches to. Okay, and how does it work? It works in the following way. So I'll quickly erase everything. So if I follow this this type of value update, so this is how it's going to look. So assuming my gamma here is assuming my gamma is 0.9 for this example, just a crude number for computation. So let's say if I'm at this state, okay. So my value function is I'm taking the max of this quantity. So I take the action which maximizes this quantity. So I know clearly if I take the action to the right, I get a reward of +1, and that is the maximum value possible. Okay. Otherwise, I get a reward of 0. But if I take the next action, I get a value function of 1, and I multiply it with the discounting factor 0.9. Okay. So at this state, the maximum possible value function that I have would be 0.9. Okay. This is based on this equation that I have over here. Okay. Similarly, if I were to reach the next if I were to take one step behind over here, okay, and I want to go to the if I want to reach to the next like get to the goal state, I need to choose the action that takes me closer to the goal state while adding a discounting reward to it. Okay. So here the reward I get is 0, but if I go here, I multiply it with the discount factor of 0.9, and the value function for this given state is 0.9. So in this case, here my value function becomes 0.81, and if I keep on backtracking it, it becomes, let's say, it becomes 0.729 and so on. Okay, so something like this. So you see what's happening here is the farther I am from the goal, my value function decreases by the factor of gamma. So this is the advantage of introducing this gamma parameter in the Bellman equation. So your agent sort of has a direction towards the goal that it needs to move to, and this is agnostic to the different initializations that the robot can take in the system. Okay, so this is some sort of an intuitive example to make you understand the Bellman equations. So I understand the notations here and the notations used in the previous slides may be different, but it's just supposed to be an intuitive example. Okay. Next is the Bellman optimality equation. So if I have the V pi for each states, I can generate the optimal policy in the following manner. So my optimal policy looks like this. Okay, so my optimal policy is nothing but the argmax of all the value functions of all the V pi for each given state, and I do this for all state. This is a pointwise accumulation of the value functions. So I'm taking the argmax of all the possible value functions for each given state, and that gives me my optimal policy. So here note that the optimal policy may not be unique because I'm using the argmax function over here. So I can have multiple optimal policies, but the catch here is that the optimal value function, which is the max of our pi of all the V pi s, this value function is unique. Okay, so I can make this claim that my V star is unique in a given MDP. Okay, so there's a subtle difference. There's a small difference that can be very confusing at times. The optimal policy is not unique, whereas the optimal value function is unique for a given MDP. And the way you can look at it is because of this argmax function. So the argmax function doesn't necessarily return a unique value, but you can have multiple optimal policies. Okay. So similarly, if I were to write down the Bellman equations for the Bellman optimality equations. So for the Q function, so for the Q functions, my Q, sorry, my Q star of S of A is the max over all the possible pi's over all the Q functions, which is this value times the times the expected reward if I am at state S and I want to move to state S prime by taking action S, plus the discount factor and the V pi of S prime. Okay. So note here that this max of pi operator is directly operated on this V pi function over here. So this max pi is not applicable to any any of these quantities, but it directly take is hit over here. So what I end up is my max of pi of V pi is nothing but my V star. Okay. And if this is understood, so in the same way, I can define my V star of S as nothing but the max of A over my Q star S of A. Okay. So one intuitive way to think about my Q star function is that if I take action A, after that, what is the optimal way to reach my goal state or my terminal state? If I take action A, so this way Q star functions can be defined for even suboptimal policies, but V star of S is only defined for optimal policies. And the way you think of it is that Q star is if I take action A, the first action I take is action A, and after that, whatever action I take is the optimal, is the I follow the optimal policy. Okay. And what V star of S does is it basically tells me that the first action that I take in Q star of A, I take the max of that action. So essentially, I'm following the optimal policy from the start itself. Okay. And yeah, this is my V star of S. And if I were to write it in its general form, so I just expand this Q star. Plus my V star of S. Okay. This is the optimality equations for my Bellman equations. Okay. So this was all that was covered. This was covered in week 4. Now, once we show that, next what Professor focused on was to show the convergence of the policy to an optimal policy. This is important. So the way you look at it is some the Banach point here. So moving on to that, we define a Cauchy sequence. Okay. And before going to a Cauchy sequence, we start off with the MDP definition. So if I have an MDPM, it's a 5 tuple. It consists of the state space, the action space, the model of the system, which is the transition probability, the expected point reward, when I move from state S to S prime taking action A, and gamma, which is the discount factor. Okay, and my Bellman equation looks like this. My v pi of s is this quantity over here, and my v star of s is v of s bar s comma a plus no plus the expected reward I get. Yeah, this is my v star of s. Okay, so this is the Bellman equation for the value function v, and you have certain assumptions you make in this proof. Okay, I'll just list it down. So there are a bunch of assumptions you make. First assumption is that the optimal policy is deterministic. Okay, what we mean by that is my policy pi of a given s is simply pi of s, because the action that I take is deterministic. So rest all other pi a by s becomes 0. Okay, so this is what I mean by a deterministic policy. This is one assumption, and the assumption is another assumption is that if MDP has an optimal policy, then there exists a deterministic optimal policy. Okay, this is another big assumption that you keep. And the third is that the MDP that you're dealing with is a finite MDP. Okay, so by finite MDP, what we mean is that my states and the action spaces are finite, and the expectation of the point reward that I get is bounded. Okay, so these are the set of assumptions that you make, and then you basically define all these value functions in the v state. You might want to refer back to the lecture if you want to get a clearer idea about the entire mathematical proof. Okay, and okay, so the to define the Cauchy sequence, the Cauchy sequence is defined as follows. So for sequence x1 to x of n, if I have a sequence, so for every positive real number epsilon greater than 0, there exists an n belonging to the set of positive real numbers, such that for every 2 point that I select which are greater than n, the elements in the sequence become closer and closer, and it is always bounded between epsilon. Okay, so what it says is beyond a certain threshold, the successive elements that I get in the sequence, they get closer and closer to each other, and eventually they converge. Okay, so I can say this as I can say this as successive elements coming closer to each other. No, this is what you mean by Cauchy sequence. And just to give an example of how a Cauchy sequence looks like. So if this is my the x-axis is the n and the y-axis is the x of n, so my Cauchy sequence, one simple example, looks something like this and this, and eventually it sort of converges. Okay, so if you notice here carefully, you see that the elements get asymptotically closer and closer as the sequence keeps on moving forward, eventually converging at a particular point. Okay, so this is one simple example of a Cauchy sequence. If I ask you any mathematical function which is a Cauchy sequence, a very simple example would be this function. So f of x is equal to sine of x by x. This is a very simple example of a Cauchy sequence. Okay, this is, I should write example of a Cauchy sequence, right? And if you were to look for any real world example of what a Cauchy sequence is in the real world scenario. So if you have studied physics in your high school, if you must have heard of something known as a damped harmonic oscillator. Okay, a damped harmonic oscillator follows a Cauchy sequence, and I should add a discrete damped oscillator because the sequence is a set of discrete points, right? So this is another real physical example of Cauchy sequence. Okay, so once you have defined the Cauchy sequence, next we take a look at the Banach fixed point theorem. Okay, this should be a capital B because proper name. Okay, so the Banach fixed point theorem definition goes like this. Okay, so suppose U is a Banach space. So by Banach space, what I mean is, or what Banach, how it's defined as. So a Banach space is nothing but the complete normed vector space. Okay, so this is the definition of a Banach space. So suppose U is a Banach space, which is a complete normed vector space, and T is basically a contraction mapping. Okay, so contraction mapping can be defined as, so you can say that T is a contraction if any two elements, okay, if I apply this linear operator to any two operators, so the distance, so that's space, the place where I'm mapped to, the distance between the two map points uh, is lesser than the distance between the 2 points initially by a factor of lambda. So here lambda is between 0 and 1, and this is valid for all UV belonging to the Banach space. Okay, so this is what I mean by a contraction mapping. This whole thing can be said to be a contraction mapping. Okay, and yeah, so there's a you can see the proof in the lecture. So if I have a sequence, so if I have a Cauchy sequence, then eventually it should converge to a fixed point, and Banach fixed point is basically one of the simplest fixed point example, and it's easier to prove. So that's what the lecture proof takes a look at, and then eventually you end it by saying that if you have a Cauchy sequence and eventually you know that it converges to a fixed point, all you need to show is that my L pi operator. So all I need to show is my L pi operator is a contraction. I should show my L pi operator is a contraction mapping, and if I show that, I can claim that the MDP that I have has an optimal policy. Okay, so before that, I should probably define what I mean by L pi, the L pi operator. So L pi operator is a mapping from my V space to the V space. My V space is a value function in the space of the value function, and the L pi operator looks like this. So if I operate it on the value function, this is the R pi, the current reward that I get, plus gamma times P pi, which is the probability of moving to the Jth state from the S state, and this is how the contraction, the L pi, sorry, the L pi operator looks like. And if I operate L pi on V pi, I eventually end up on the V pi function itself. So here I can say that my V pi is a fixed point on L pi. Okay. So what we mean by fixed point is, suppose I have an operator, say B. Okay. So if I operate it on some vector X and I end up with X, so I can say that X is basically a fixed point on B. Okay, so this is unrelated to what I had written on top. This is just me giving you definition of a fixed point. So this is what we mean by a fixed point, and can think of it as finding roots of an equation. So if I want to find a root of an equation, I typically equate it to 0. So if I have, let's say, f of x is equal to 0, so that means to find the solution, I need to find the roots of the equation, which gives me the solution. Okay. Similarly, if I want to find the solution for a fixed point, equation, so a fixed point equation typically looks something like this. So any linear operator has no effect on the input, on the output. Sorry. So you can simply represent it by some another function g of x, and this is also you can convert it into a root finding equation. So this is how typically you solve the fixed point problem. Okay. So eventually, all you need to do is to show that this L pi that I have is a contraction mapping. And once you show that, you can directly relate it to the MDP problem and show that my MDP that I have it converges to an optimal value function. Okay, this is the entire point of this lecture that was covered in the class. So the proof, again, you can find it in the class lecture. I should probably write down the important result. So just the important result is that L pi is a contraction mapping. Okay. Refer to proof in lecture. Okay, you should take a look at it. And what we mean by that is that, so L pi of V of S minus L pi of U of S. So these are any 2 points on the V space. If I select any 2 points from the V space, which are U and V. Okay, and so I say that this function So the contraction mapping works as in such a way that if I select any 2 points in the V space, V and U, so the map distance between the 2 points is always less than the total maximum distance between the vector V and U in the V space, and this uh, by a factor of gamma, of course. Okay, so here you see that the gamma here corresponds to the lambda that was defined in the previous slide in the Cauchy sequence theorem. Sorry, in the fix. No, yeah, in the contraction mapping part. Okay, so this here corresponds to the gamma over here, and the gamma here is my discount factor of the MDP. Okay, so this essentially shows that my MDP has converges to an optimal value function. That's the entire point of the exercise that was done in the class. Okay, so I think this was all that was there for week 4. I had given you this this problem. Yeah, this MDP modeling problem. It's a take-home problem. So you can design the MDP. You guys have already done 2 example problems in Aniket's TA. So do this MDP and try to answer these 3 questions. This is one take-home assignment that you can have. And next take-home assignment that I want to introduce you is basically this problem. Okay, so I don't expect you to basically come up with the answer in the next week itself, but I wanted to just take this example and keep on building it on so that you have an idea about designing the environment or designing the MDP or the reinforcement learning problem. And later, as we move along, you can try out different algorithms that are being taught in class. So be it policy search, be it policy gradient, be it SARS or Q learning, which you will encounter later on. Okay, so this is how the problem looks like. Okay, so this is a particular problem that I have designed. I basically came up with this design. So this, I'll call this as I'll name this environment as the warehouse environment. Okay. It's a very simple example. So inside the warehouse, there is a delivery agent, and the agent has to deliver the box from its location to this target position. So the agent has to come here and deliver the box here. But the catch here is that the agent cannot lift the box. The agent can only push the box. So the agent can't lift box. Agent can only push box from behind. Okay. So this is a very popular game. This game is known as the game called Sokoban. I don't know if you guys might have played it in your video game console. So the idea here is that the delivery agent needs to come here, go here, here, then push the box. So the agent pushes the box here. The agent goes here. The box reaches here. Then the agent reaches here. The box reaches, say, here. Then the agent has to travel here, and then here. Then it pushes the box here so that the box reaches, this goal position. Okay. So this is the basic idea of the task that you need to do. So you need to design this sort of an environment. Okay. So the problem here comes is when the box you have, it gets stuck in a state where it is unable to move forward from. So let's say if somehow the box ends up in this part. So that means the game essentially ends, because after that you can't push the box outside of this corner. So this is an undesirable state. So you don't want the box to reach in this particular state. Similarly, any such state here. So the agent can come here, but the box should never reach in this state. So these are like some undesirable states that the box should never reach. So you need to design the MDP problem, and I think you can just copy paste the environment in your Python code. So this is basically a uh, grid world kind of a problem. So I have 1, 2, 3, 4, 5, 6. I have 6 columns, and I have 1, 2, 3, 4, 5, 6, 7. So this is a 7x6 grid world problem. So the agent can take actions. The actions the agent can take is okay, up, down. This is right, and this is left. Okay. So these are the actions that the agent can take. So you need to design the MDP as such. You have all the ideas. You have been well introduced to the concept of MDPs. So you can accordingly define the state space. I have defined the action space for you, but yeah, the action space is the up, down, left, right, this thing. So you have certain states that you don't want to go, and yeah, so you can try to design an MDP around this problem. You can use your Python code or do it by hand. And basically what your code should come up is the policy that should look like this. I think this is the policy here. In this case, the agent following this path, I think, is the only policy. Uh, I don't think the box can reach the goal in any other way. So in this case, the optimal policy is unique, but it need not be the case. If I change the environment, the optimal policy, there might be multiple optimal policies, but I think for this particular example, uh, the optimal policy looks like this. Uh, if not, you can correct me. I might be wrong. There might be other optimal policies that I am overlooking right now. But yeah, so this is the task that you need to do. So this is, instead of a word problem based environment, this is a game based MDP that you need to design. So you keep a track, you keep a copy of the MDP that you designed, you create the environment on your own, and later on we'll try out different reinforcement algorithms as we learn on this particular environment. So this is a simple environment. You know what the agent needs to do and where all the box needs to go to reach to the goal position. Okay, so I think this would be a very good exercise. So you just continue with this, and we can pick it up in later weeks as we learn more and more new things. Okay, so this is like a, what I can say, this is uh, a long takeaway assignment. I don't know, maybe long takeaway question. Okay, because I'll keep coming back in the later weeks when we learn different things and we see how we can apply whatever we have learned to this example over here. So I think you should take a look at this and design the problem. And yeah, I think that's pretty much what I had in mind for today's class. And to end this thing, I think, as is the tradition, we just quickly discuss the week 4 assignment 4 questions, all the non-graded ones. Okay, so I'll quickly breeze through the question. First question is like pretty straightforward. So you just need to select the correct Bellman optimality equation. So you see that, okay, I should. Yeah, so if the Bellman optimality equation has a dependence on gamma, if I don't have dependence on gamma, I basically it is like dependent on the kind of initialization that I do with my agent, right? So this can't be my Bellman optimality equation. Again, refer back to the toy example that I used 5 slides ago, how the discount factor is important in my Bellman optimality equation. So my correct answer is this. Okay. Otherwise, if you looked at the derivation, you can reach to this equation again. Okay, so this is the correct Bellman optimality equation. Second question is, it's a true or false question. So in MDPs, there is a unique resultant state for any given state action pair. So this is incorrect. If I have a given state action pair, I don't have a unique resultant state. So that means my transition probability is not deterministic, but what I'm considering to be deterministic is the policy. So the policy is different from the model. The model is a transition probability. So I can't say that there is a unique resultant state for any state action pair. So this is definitely false. Okay, then moving to the third question. So the state transition graph for any MDP is a directed acyclic graph. So just refer to the example professor had used in the class. So this particular exercise, if I am in state 1, state 2, this is let's say action 1, action 1. This is action 2, this is action 2. Okay. So you see that this is a directed graph, but this need not be acyclic. It can very well be a cyclic and still be an MDP. Okay. So the state transition graph for MDP is a directed acyclic graph, is too restrictive a statement. So that's why this is also false. Okay. Oh. And yeah. So the fourth question is, I have three statements. I need to find out which of the statements is true. So the optimal policy of an MDP is unique. Again, this is incorrect. The optimal policy is not unique, but the value function, the optimal value function is unique. So option 1 is incorrect. So I just quickly eliminate all the options showing statement 1 to be correct. Okay. Second is, we can determine the optimal policy for an MDP using only the optimal value functions V star without accessing the MDP parameters. No, that is not true. You can determine the optimal policy by only accessing the Q star value functions, because V star value functions exist only for the optimal policy, but you can have Q star values for non-optimal policies as well. So to determine the optimal policy, you can do that without accessing the MDP parameters and only using the Q star value functions. Okay, so not the V star value functions, but the Q star value functions. So here only statement 3 is correct. Statement 2 is incorrect. So this is incorrect. This is incorrect. So this statement is correct. I should erase everything. So my answer here is option 3. Okay. Next is, which of the following is a benefit of using RL algorithms for solving MDPs? Okay, so if you are solving the MDPs, so you are basically taking help of the Bellman optimality equation to get to the policy. Okay, so which of these things do not appear in the Bellman equation? So that's how I can reframe the question. So they do not require the state of the agent for solving the MDP. No, that's incorrect. The agent needs the state in order to solve the MDP. They do not require the action taken by the agent to solve the MDP. This is also incorrect. Third option is they do not require the state transition probability matrix. Now, this is true. The agent need not necessarily have the model or the state transition probability matrix in order to solve the MDP. So you will find no mention of, so you don't require this in order to solve the MDP. So this is the correct option, and they do not require the reward signal for solving an MDP. So this is again incorrect. Yeah, so I think these were the 5 questions for my week 4 ungraded assignment. I think that's all I had in my mind to do for this week. Again, sorry that I couldn't do this in the live session, and due to connectivity issues, I had to switch to the offline mode. If you have any questions, you can reach out to me via the discussion forum, or you can directly email me. And yeah, thank you for tuning in. We'll meet next week on Friday from 7 to 8 p.m. And thank you. Thank you for tuning in. Happy weekend. Good night. Bye.